Greetings, students. About 2 years ago, faculty of Khan uploaded a video on the solution to the PDE problem of a simply supported vibrating beam, as you can notice here. And he did one part on that, and I think he never found a chance to publish the second part. So I decided to complete that problem. As you notice here, this PDE is second order in time and fourth order in space. And you notice that negative alpha squared coefficient, where alpha is defined to be E times I divided by mu. He explains all this stuff in his video, and I'll also put the link in the description. Here, E is the Young's modulus, I is the area moment of inertia, and mu is the mass per unit length. Along with those boundary conditions, which are all homogeneous, the displacement at 0 and L, and also the second derivative of displacement at 0 and L are all 0. And two initial conditions where we have the displacement, initial displacement, and the initial so-called velocity as functions of x. And sensibly uses separation of variables to get the solutions of for x and t, and finally combines them together to get this expression for u of x comma t, where we have beta here as omega divided by alpha to be found, and omega is some sort of eigenvalue that he finds during finding the solution to these functions cap x and cap t. And now I'm going to apply the boundary conditions to hopefully get rid of some of these constants and simplify a little bit. And I'll finish the solution to this problem. So the first two boundary conditions where u at 0 comma t and u at L comma t are 0. They mean that our function cap x must be equal to 0 at x equals 0 and x equal to L. And the other two boundary conditions mean that the second derivative of cap x with respect to x must be 0 at x equals 0 and x equal L. Since we're going to need the second derivative, I'm going to differentiate this cap x with respect to x twice. So from these two terms, cosh is back to cosh, sinh is back to sinh, and we just get a factor of beta outside. And here for the cosine and the sine, after twice differentiation, cosine turns into negative cosine and sine turns into negative sine, and we also get a factor of beta outside. So the second derivative of this cap x with respect to x is, we get c times beta times cosh square root beta x plus d beta sinh of square root of beta x minus e beta cosine of square root of beta x minus f beta sine of square root of beta x. Okay, let me get this x of x and copy it down, and now we're going to quickly apply these boundary conditions. For x at 0, we get c times cosh 0, which is 1, so it's just c, plus d sinh of 0, which is 0, plus e cosine of 0, which is 1, so we get plus e plus f times sine of 0, which is 0, and this must be equal to 0. And the second derivative of x with respect to x at x equals 0, that gives us c beta cos 0, which is 1, plus d beta sin 0, which is 0, and we also get minus e beta. Sine of 0 is also 0, so this must also be 0, and the two equations that we get here are c plus e equal to 0 and c minus e equal to 0. Since beta is not 0, as it is defined to be equal to omega divided by alpha, and omega equal to 0 does not give us a physical solution. And the solution to this system is obviously c equal to e equal to 0. And this actually simplifies our x and its second derivative quite a lot. Our x of x now reduces to d and f are non-zero, c and e are 0, so we get d sinh of square root of beta x plus f sine of square root of beta x. And the second derivative of cap x with respect to x is d beta sinh of square root of beta x minus f beta sine of square root of beta x. Now I apply the two remaining boundary conditions, which are x at L equal to 0, and that gives us d sinh of square root of beta L plus f sine of square root of beta L equals to 0. And the second derivative of cap x with respect to x at x equal L, that must also be 0, and it gives us d beta sinh of square root beta L minus f beta sine of square root of beta L equals to 0. So here we have a system of equations, two equations for the two unknowns d and f, that's homogeneous, so it has the trivial solution of 0, but we do not want that, because if we set d and f equal to 0, we just get the 0 trivial solution to our function u. And this system of equations will have infinitely many solutions if the determinant of the coefficients is 0. And by the way, in the second equation, we can just cancel this beta since it is not 0. And we get infinitely many solutions from this system if the determinant of coefficients is 0, as I mentioned, and the determinant of coefficients is negative sine root beta L times sinh root beta L minus exactly same expression. The product of these two terms is also sine square root beta L times sinh square root beta L. So to get infinitely many solutions, this must be equal to 0, which simply means that sine of root beta L times sinh of root beta L must be 0. Sinh only has one real root, and it's when the argument is 0. But since we know beta cannot be equal to 0, that's not the solution. So this means that sine of root beta L must be equal to 0. And we know sine is 0 when the argument is an integer multiple of pi. So root beta times L must be equal to n pi. And since we are getting n solutions here, one for each value of n, I put subscript n for this beta. So we get a square root of beta n as n pi divided by L. And this also means that since we have a square root term on the left, or a square root of beta n, the thing on the right hand side must also be non-negative. Beta is not zero, so the stuff on the right must be strictly positive, and it means here that n is greater than or equal to 1. We also get beta n as n squared pi squared divided by l squared. And we also had beta as omega divided by alpha. So we get omega n as alpha times beta n, which becomes alpha times n squared pi squared divided by l squared. And getting back to this system, we notice that, okay, this sine of a square root beta L, that must be 0, which means that f does not have to be 0. If that's the case, since this sinh term is not equal to 0, this means that d must be equal to 0. Okay, perfect. So now for our function x, we just have one unknown coefficient. Since d is 0, we just get x as f times sine of root beta x, but we have n of these solutions, so I put subscript n here, there, and 1 for beta. And the solution to the time part, or this cap t of t, which is a times cosine omega t plus b sine omega t. We also get n of those. So Tn of t is a n cosine of omega nt plus bn sine of omega. And our solution, x times t, or x sub n times t sub n, we get fn an sine root beta n x cos omega nt plus fn times bn times sine root beta and x sine omega and t. But since those are just constant, I can just pick new variables. We get two constants in our solution, and it makes sense because we only have two initial conditions to be used for finding those constants. So I write x sub n times t sub n as some new constant, let's say g sub n, cosine of omega nt plus h sub n sine of omega nt, and all of this multiplied by sine of square root of beta nx. And we got the square root of beta n as n pi over L. So here, instead of a square root of beta n, I'm going to put its equivalent expression, which is just n pi L over x. So I'm quite sure now that this reminds you of the Fourier series. We're going to get a Fourier sine series as the solution to this problem. And it makes sense because the u and its second derivatives are 0 at the boundaries, and it's only the sine function which satisfies all these conditions together. And finally, our u of xt, our final solutions. So it's worth to note here that this is actually some u sub n of x comma t. And the full final solution would be the linear combination of all these un's. We also discussed that n has to be greater than or equal to 1. So the solution to the PDE is this infinite series as n runs from 1 to infinity of some gn cosine of omega nt plus some hn sine of omega nt, all multiplied by sine of n pi x over. And now we only have the initial conditions, the initial displacement and initial velocity in hand to find gn's and hns. We know that u at x comma 0 is some u naught of x, and that's equal to the series as n rounds from 1 to infinity. So if t is 0, this term vanishes, the sine term goes away, and cosine is 1. So we get gn's times sine of n pi x over L. So gn's are the coefficient of the Fourier sine expansion of the function u naught of x. I don't go through all the details that you have to multiply both sides of this by some sine of m pi x over L and then integrate from 0 to L and use the orthogonality or to show that you get non-zero terms only for the case where n and m are equal. I believe that you know all of these. And finally, we get gn as 2 over L times the integral from 0 to L of u naught of x times sine of n pi x over L dx. And since x is just some letter here, and I want to put all of these together in the final version of the solution, I'm just going to use x prime instead of x, just for beauty purposes. Then we have the condition of initial velocity to apply, and for that we're going to need the first derivative of u with respect to time. So we're going to differentiate this series with respect to time. So we get infinite series as n rounds from 1 to infinity of negative gn omega n sine of omega nt plus hn omega n cosine of omega nt times sine of n pi x over L. And if now we set t equal to 0, we get the first derivative of u with respect to time at t equals 0, and that's given to be v naught of x. As you notice, if we set t equal to 0 in the summand, this zeroes out and we just get hn omega n times cosine of 0, which is 1. So finally we get the series as n rounds from 1 to infinity of hn multiplied by omega n multiplied by sine of n pi x over L. And now the coefficient of this Fourier sine series are hn omega n's equal to 2 over L, the integral from 0 to L of v naught x prime sine of n pi x prime over L dx prime. So for hn, to get hn, we need to divide both sides by omega n. So finally, we get hn as 2 over L omega n times that integral. Now let's put all of these together and we can write the final version of the solution to this PD. And by the way, omega n, if you remember, is alpha times n squared pi squared over L squared. So the final solution, since we have gn and hn here and both of them have a factor of 2 over L, so I'm going to take that common out. We get 2 over L times the series as n runs from 1 to infinity. For gn's, we have the integral from 0 to L of u naught times sine of beta n's. So we get the integral from 0 to L of u naught x prime sine of n pi x prime over L dx prime times cosine of omega nt. So we get cosine of alpha n squared pi squared t divided by L squared. For Hn, we have 2 over L omega n. 2 over L is already factored out, so we get 1 over omega n, or we can write it as L squared over alpha n squared pi squared times the integral from 0 to L of v naught x prime sine of n pi x prime over L dx prime. And it should be multiplied by sine of omega nt. So sine of alpha n squared pi squared over L squared times t. And all of this must be multiplied by this last term, which is the sine of n pi x over L. And okay, great, we're done.